How are you guys?
Good. What about yourself, sir?
Yeah, not too bad, not too bad.
Good.
It's getting close to the end. So,
Yeah.
mm. Did you get a chance to do that test?
No, I just had a look at it now. I'll do it after class.
Yeah, okay. Oh, there's a particular question I just want to run through. Maybe I forgot to mention that. Let's try this. How many people send the answers? Light and matter. Yeah, good number of responses. That's good. All right. Let's just find that photoelectric effect. I just got run through the matter waves, how to do matter waves type questions. Some people are pretty good at it. Some are still struggling. Maybe I'll quickly go through like a summary, how to deal with those questions. I'll skip some of the questions are quite simple, straightforward. I'll skip them. Some of the questions are like recent exam questions. I have the marking scheme again. Just look at whether you guys are getting the right answer. Go through few theory questions. There are some theory questions can be 3 marks, could be 4 marks. There is a one question up to 6 marks. So just to go through that question as well. And then we'll look at the last bit of energy level diagrams and Bohr model. All right. If you guys can find that worksheet with photoelectric effect and matter waves, we can't go through every single question, but we'll go through some questions. You can give it a try, the 2018 exam question, and see there, again, like last week, there's this range of answers, and see how well your answer is matching. And there's an explanation question as well. So I got the answers from Yenoli, got the supplied the answers. I didn't see any of the other guys. Okay, guys, if you can find that worksheet, it's called photoelectric effect and matter waves 1. I got the answers from Dinaru. That's good. I can't remember. Shuka's answers are there. People didn't get a chance to supply those answers, guys. Just take half an hour, 40 minutes, and then supply those answers, please. Yeah. Okay, I'll quickly recap. I think you guys know when you try to have these two identical diffraction patterns, one is produced by X-rays by shining the beam of X-rays into a crystal. And if you have identical spacing supplied by electrons, our conclusion is, what we're saying is the spacings in the diffraction pattern proportional to the wavelength. to lambda. So therefore, identical diffraction, identical spacing means they have the same wavelength. If they have same lambda, one is a normal wavelength, that's a de Broglie wavelength. If they have same lambda, they have the same momentum as well. I think I included G.P. Thompson's original paper. He's reported about matter waves. By that time, Davison and Gama already reported their work. He was kind of a little bit critical on their work. They said that it wasn't. Oh, you can't hear. Can you? Other guys can hear me? Yeah. Okay. All right. Okay. That's good. Excellent. So now I don't know, I can't remember whether I just put that equations. Now I talked to a few people who try to do their SAC on this in recent time. Some people got really confused with the photoelectric effect and matter wave equations. Some equations you can use it so that they're thinking about the kinetic energy of the electron. Here we're talking about confusing with the EK max. I just felt a little bit uncomfortable after hearing that. So remember, we're talking about these waves produced by particles. That's why we call them matter waves. So when you have, especially when you have identical diffraction patterns, so you have a beam of photons, like mostly X-rays. And then you're producing a diffraction pattern by electrons. Okay. Now, if that's the case, their wavelengths wise, so photon wavelength is lambda equals C on F, or you can use another connection with the momentum as well, H on P. Okay, we're talking about light here. This is the momentum of light. In terms of energy, for the electron, wavelength is de Broglie wavelength, H on MV. H on MV. And in terms of energy, photons can be found using H on lambda, HF. Or E equals PC. Do not use E equals PC for electrons. When you come to electrons, you can use just the kinetic energy. We're not even considering the relativistic effect here. There is, but we're not ignoring that. Or you can write EK as P squared on 2m as well. Or in fact, you can write another way, because your de Broglie wavelength, H on MV, your momentum is H on lambda. So we can just modify that to H squared 2m lambda squared as well. Sometimes comes handy. I don't know if you guys can see it. 2m lambda squared. 2m lambda squared. That's again the momentum. Kind of I included that on the top. Momentum can be written as for photons, P equals H on lambda. This is P equals mv. And again, you can say P equals H on lambda works here as well. Then if you have the identical diffraction pattern, identical spacings in the diffraction pattern, identical. identical spacing in the diffraction pattern. If their spacings are identical, their lambdas are same, the momentums are same. But if they ask you to explain why they have the similar identical spacing, you don't need to bring the momentum, because basically you can just simply say that. You can say that electrons show wave behavior. It has a wavelength. Spacing in the diffractions are proportional to lambda. Identical spacing means same lambda. That's enough to cover, to explain why they have identical spacings. So momentums are same. And they have same energy. But their energies are different. Certainly different. We show that energy kind of relationship. Okay, Phil, I'll just skip question 8 and 9. I think I put the answers, expected answers for question 8 in your front page. This is the photoelectric effect and matter wave worksheet. I'm not going to do this one. You guys need to do it. These are the expected answers. That just simply use, they're asking, determine the wavelength. So the energy is given. You can just say epsilon lambda. Question 9, they ask you to find the momentum. When you come to momentum, that's 6.63, negative 30. Okay, my main focus is do a couple of questions and then go back to these theory explanation questions. But there are 4 marks or 3 marks, 6 marks questions are there. Just have a quick check on that. People having trouble connecting. Okay. Then next thing, again, this is 2018 question. I have the marking scheme. Give it a quick try. Don't spend too much time. Get your answers. I'll give you the range of answers you have. Very quick. That's explanation 1 as well. Which H value we can use for the, okay, it depends on the question. Whenever come to momentum or mass, you have to always use 6.63. If they, for example, this question, they're giving energy in kV, ask you to find the wavelengths. In that case, you can use 4.14. The next question, they ask you to find the momentum, then you have to use 6.63 because momentum has a units of kilogram meters per second. So you can't use electron volts there. But when you come to electron volts, and that's electron volts, then you can find that. Yeah, Yash, you had to very clearly that differentiate that electron produce diffraction pattern if they are particles. Does that particle split? No. It's just behaving. The particle is just shedding its particle behavior. It's no longer acting like a particle anymore. So no, because it's like it have a 2 lives. Okay, so it's a dual life. Okay, so it can behave like a particle. Whenever come to a slit, it doesn't behave like a particle anymore. That's why we call it dual behavior. It just have a different coat, different suit. It's just wearing a different suit now. So it's purely acting like a particle there. So it's rather than that passing through like a particle, it's passing through like a wave. So that means it's trying to produce ripple here. Making ripple means producing vibrations there. And then those vibrations can interfere destructively. Yeah, just become a wave. So just have a dual nature. That's why I'm saying they were at the beginning, they were saying, can we find one experiment that they can show both behaviors? It's so difficult. And one of the scientists at the end said that, okay, the these are for the light behavior. Light has both behaviors as well. So they say, okay, Monday, Wednesday, and Saturday, it's behaving like this is like a funny story. Like they talk about that as a wave, and then the other days it's acting like a particle. This is just to describe how difficult it is to differentiate the two. But only way that you can differentiate by looking at different situations. When you come, say, for example, light, when you come to interference, you can't explain unless you bring the wave behavior. When you come to photoelectric effect, you can't explain unless you use the particle behavior. In the matter, it's the same thing. So particle behavior is easy. It has a mass, it has a momentum. But when you come to diffraction, you can't really explain unless you bring the wave behavior. Yes, that's why we call wave particle duality, dual behavior. Okay. No, this is where, so this is where they think about like when they talk about electrons, orbits around the nucleus, right? So you have the neutron proton, electrons are moving around. Initially they thought, okay, electron is like nicely very defined path there. Later on, they realized that electron doesn't have this very defined path. You can have a certain probability where it can live. Then realize that it's just making like a wave, acting like a wave rather. So they were started to talk about rather than orbits, they're talking about orbitals, yeah, in chemistry. So there is a probability where it can lie, but we cannot exactly say where it's going to sit there. So it's basically it's acting like a wave moving around. But when the electron is stationary, yeah, that's very easy. That's a particle. It's not moving. Even when it's moving at like a very slow speeds, it doesn't show its wave behavior significantly. But when you're traveling very high speeds, that's where the problem comes in. And then that's where its wave behavior kicks in. Okay. So that's why I call wave particle duality, dual behavior. Okay, so next question, guys. That answer is 22, in fact. As a rule of thumb, whenever you're calculating the momentum, your values should be in the ballpark. Correct? Value should be, can vary between that to that, maybe roughly. So if you get a value when you calculate like negative 48 or something kilogram meters per second, you definitely need to double check your numbers. If you get a value like negative 6 or something, you definitely need to check your numbers. This is just to ballpark, just to give a feel what number you're expecting. Okay. Can someone give me what answers you guys are getting for the 2018 exam question? Now, first question says, so the students are doing an experiment. They're measuring EK max or VS versus frequency. You have a graph. Now, the next thing, with 6 times 10 to the power 14, the ammeter always shows 0. So Sai want to repeat the experiment for this frequency with much greater brightness, and she want to expose the time much longer. So you want to increase the intensity, increase the time. Kim says electrons will never be ejected with this frequency of light. Now, asking who is correct? This is in page 3. It's continuing from page 2 to 3. Whether it's Sai correct or Kim is correct. Because by understanding the wave particle behavior or particle model of light, we know that there is a threshold frequency. So Kim says photoelectrons will never be ejected for this frequency. She's right. You have to say Kim is right. Kim is correct, you get 1 mark. Now the question they are asking, what explanations might Sai give to support her opinion? Why she's saying keeping longer and brighter? She thinks that light can be that light can be eject the photoelectrons. They're asking what expectation might be Sai give to, or explanation Sai might giving to support her opinion that by waiting longer and using a brighter light source, photoelectrons could be ejected from the metal with a frequency of 6 times 10 to the power 14. How are you going to answer? It's a 2 marks, not much. How are you going to answer, anyone, to get the full 2 marks? Tatum, Rasindu? Believe it's in a wave model. That's true, but rather than we mention about a wave model, we simply asking why she's saying that. Why she's saying that. So you need to get the essence of wave model, and just without mentioning about, you don't need to mention about the wave model. You can just mention by implies constant energy transfer, energy, gradually give energy to the electron. That's kind of correct. Okay, let's run with this answer. Should by a wave model have this based on a wave model nature of light, assume that for high intensity longer time will provide sufficient energy. Yeah, so you can simply say that by giving supplying a brighter light and exposing longer, she believes that the light will deliver more energy to the electron. That's all you need to say. And once electron gains sufficient energy, it can eject. That's what she believes in. Okay, reject. I think, yeah, Patham's kind of covers as well. So wave model increasing the intensity, increase the average kinetic energy absorbed by increase the intensity, increase the average kinetic energy absorbed by each electron. And we're talking about average kinetic energy in terms of the, when you say average kinetic energy here, you're talking about the average kinetic energy of the electron in terms of the oscillation. I bit unclear about the word when you're saying increasing the intensity increases the average kinetic energy absorbed by each electron. Okay. Okay, and individual electron will accumulate enough energy. Yeah. So you're saying that electrons start vibrating more faster? Could be true, but that's what the temperature is telling. It will increase the energy over the time period. The energy should increase until, yeah, I think Sandra's answer is pretty good. Okay, what you have to say? Increasing brightness and time. So I believe the light can deliver more energy. To the electrons. So the electrons can, once electrons will, these energies can accumulate. On the electron, and once it reaches and once it gains sufficient, it will eject. That's what Sai believes. That's her argument. This energy can accumulate on the electron, and it gains up once it gains sufficient energy to eject. That's what she thinks. But that didn't happen. Okay, that didn't happen. But to get the full 2 marks, you had to say that she believes that supply more energy, and once it gets sufficient energy, it will reject. Hey guys, can you get the answer for this and then see it's within the range? Question 5. B, part B. That's a range. I think that's a generous range here. At the same note, try question part C as well. B and C. Yeah, I think that answer is good. Here, both answers are okay. They are within the range. Yep, make a habit of giving the energy. Hey guys, EVS, okay? EVS, not EV. Okay, those numbers are good. Yep, that's good as well, Sunraj. Yeah. Pathum, your answer is good. Remember to put the units. Yeah, it's good. So the expected answer for part B, guys, 5.5 is the expected answer, negative 15 EVS, but the range is 5 to 6 basically. That's the range. If you get the answer between here, it should be fine. So remaining questions, you had to use that number, okay? Okay. All right. Next question. So part C, you're just using the Planck's constant. So you have used the value that you obtained before. So 5.5 times 10 to the power negative 15. The threshold frequency was like 6. So your answer should be around 3.5 plus or minus 0.5. As long as your answer is within that range, you should be fine. Okay, thanks. Okay. Okay, next question. You guys can quickly work it out, part A and B. Quickly, question 2. Get the answers and see if you guys are getting the right answer. They have like exact answers. There is no range on that. Question A and B part, the identical diffraction pattern question. So people are still not 100% on these questions. The first part, just find the lambda using HC on lambda. You don't need to convert, it's all in electron volts. So you can use electron volts second, find the lambda. Part B, you have the option of going on the path of, they ask you to find the kinetic energy of the electron. Since you're finding your lambda there, easiest one to go with that. Some people can go with the path of momentum as well. Mass, then your number should be that. Whenever you come to mass in kilogram or momentum, you go with that. When you give the work function on when we leave, yeah, don't put the negative. Yeah, just put the positive value. Just get the magnitude of that. Okay. Even if you put the negative, they're not going to penalize it, but just put the positive value. Yeah, give the positive value. Yeah, sure. I think I got the answers from Pathum. I got the answers from Dinura. I got the answers from Ishuka. I can't remember Nindu's answers. I can't remember the name. Yep, that's good. Pathum, that's good. Sunraj, good. Are you allowed to use the derived equations immediately without justifying this one? If you write this equation directly like that, they gave a 1 mark. They gave 1 mark in 2018. Just write in that. What you can do, you can keep that and then use that just to save your back. So do that. They gave 1 mark for that. Generally, they are pretty good, like writing this equation. Probably get directly 1 mark without, but to save your back, just say that P equals H on lambda. Then do that. It definitely 2018. I think I put the marking scheme in the back. They give 1 mark for just writing that equation. Oh yeah, either that or that they give 1 mark. Either that or that they give 1 mark directly. So that's derived formula that they're expecting you to derive it beforehand in your cheat sheet. So give 1 mark for that. Yeah, you can see here. You guys can see that the first line on the top, second line. So P squared on 2m or H. Actually, they showed H lambda squared on 2m. They give 1 mark for that. So they put H lambda. Okay. All right. So your answers are, guys, should be question 2A. You should have a value of this one. Should value of 0.155. If you leave it like 1.55 negative 10, you lose a mark. Because you need to show in nanometers. Here B, you have to have value that negative 17 joules. Find the wavelength, that, sub in here, and then you get that. So we use 6.6. Yeah, when you have momentum, and also in the equation, if you are dealing with mass, you always put 6.63. Okay. The situations where they give the energy in electron volts of, say, X-rays, ask you to find the wavelength, then you don't need to put 6.63 because the energy is in electron volts. And then you can use the Planck constant in electron volts second, and then you can work out the wavelength. When you come to momentum, or if your equation involve mass, like situation like this, you just have to use 6.63. All right. Can you guys quickly get through question 16, part A, B, and the theory question? That's main interest. And then after that, we'll jump straight to that 6-mark question, and then we'll finish it off. And then finish it off our emission absorption spectra. The next question, they're giving an experiment. You're shining particular light, has a frequency 7.13, 10 to the power 14. And the work function is that. Ask you to find the stopping voltage. The next question, they ask you to find the longest wavelength. Yeah, Pathum, that's correct. Sunraj, you got the answer. Is that the, yeah, the previous question. That's correct. Yeah. The answer for part B has to be 1 times 10 to the power negative 17. You had to put the mass of an electron. The Planck constant should be 6.63, and the wavelength that you obtained from previous question, which was 0.155 something. Yep, Sunraj, that's correct. Anyone else got the stopping voltage, guys? Ishuka, Afra, Josh, Litara, Manik, Vitura, anyone else got the Ramudu? Generally, you guys already got the answer? Okay. So remember the stopping voltage is same as EK max. So you can simply use HF minus the work function here. We using the fact that in electron volts, they're both same. Yeah, it should be. So that's 4.14. The frequency was 7.13, 10 to the power 14, and minus 1.95. Should get like 1. The longest wavelength corresponding to related to threshold frequency. So you can find lambda C on F naught. So it should be 2.88 negative 7 meters or 288 nanometers. Now keep in mind the exam, they're expecting you to sub it in every number. Okay, it's not showing here. You have to show all the numbers you're subbing in. That's 1 mark, and then answer 1 mark. In this case, 3 marks. So you have to show, so you use the equation, the numbers, how they give the 3 marks here. Yeah, identifying that your EK max is same as VS, you get 1 mark, and then that 1 mark and final answer 1 mark. Okay, next question. This is how the question goes, part C. In her third experiment, April changes the metal plate from zinc and used platinum. Platinum has a threshold frequency 1.53 times 10 to the power 15, and she is still using a frequency of 7.13 times 10 to the power 14, which is less than the threshold frequency. but does not make any other changes. So April observes for a longer time and then increase the April observes for a longer time and increase the intensity for the light beam. Still find that the photoelectrons are not emitted. Explain how April's observation supports the particle model, but do not support the wave model. So to answer that, you need to talk about the predictions in particle model and then how that align with April's observation. Then you had to talk about predictions in the wave model, why the wave model failing in this context. So there are three key points you need to explain, because you have to explain why, although April was shining the light for a longer time and also increasing the brightness, that did not help reject the photoelectron. So you need to mention about how the energy is delivered in particle model compared to wave model. Wave model, it's a continuous, energy can accumulated. But we know that in particle model, each photon given energy into one electron. So that part has to be mentioned. So 3 marks. So first you talk about particle model predictions and then how April's observation aligning with that. Particle model predicts the presence of threshold frequency, because the wave model doesn't consider threshold frequency. Threshold frequency. Okay. So below this, no photoelectrons ejected. No photoelectrons ejected. No matter what's the, regardless of how high the intensity. Intensity or longer, or how long you exposed to. Exposed. So this is what April was observing. This agrees with April's observation. There is no continuous accumulation of energy here. Next thing, wave model. Wave model predicted that the energy supplied by the light intensity amplitude or intensity. And the energy can be accumulated. Accumulated on the electron. One electron. Once electron gains sufficient energy, it can eject. However, this wasn't observed. Wasn't observed in April's experiment. Now, wave particle model further predicted that energy of each light particle, energy of each light photon is related to the frequency, and each photon supplies energy to one electron. And no accumulation. Accumulation of energy. So these observations are consistent with these predictions are particle models predictions are consistent. April's observation. Okay, particle models predictions are consistent with April's observations. So first of all, we said that one of the predictions is the presence of threshold frequency. And here wave models predictions, they said wave models light energy is related to the intensity and then can be accumulated. But we see that it's not working that well. And when particle model again saying that energy you can supply one photon to one electron. You can't add up one photon to one electron. Okay. Question 13. Do a quick try. So you have a accelerating potential. Just like electric field knowledge. The electron is coming out with a certain energy. The work done by the electric field. It's Q times delta V, which is capital V here. Q times capital V, don't mix up your V's here. That's voltage is equal to kinetic energy half mv squared. And they ask you to find the momentum or de Broglie wavelength. You have to find the either speed or momentum and sub it in here. When you sub in here, yes, it has to be 6.63 this place. The reason is we have mass here in kilograms. That's electron, 9.1, negative 31. Either you can find the speed or you can find the expression for mv directly. You get that. Q is the charge of an electron. I gave everything there. 9.1 negative 31, sorry. And find the speed. Maybe speed or MV and then sub it in. If you go in the path of the speed, you should get a speed of 3.75 times 10 to the power 7. And plug it in. People trying to find the momentum straight away. You can do it. You do by times both end sides by 2m. And then you can use that for the momentum straight away. That's another way of doing it. The final answer should be nanometers. If you leave the answer in meters, you get a use 1 mark. It's a 3-mark question. After that, we'll jump into the 6-mark actually. After that. Can we write the derived equation straight away from the voltage and wavelength? Even here, at least I would show that. Then I can write it like that. If you write the two connections, that, and then show that is 2mqv capital V. I don't write in one step, at least just show that and that. Might be okay, just to save your back in case. Okay. Question 16. Very quickly get the question 16, guys. Expected answers. Let's see. That's also range of answers. Let's see what you guys are getting. Maybe I'll put the answers, see where you guys are getting those answers. Yes. Part B. Did we go through the same question? It's like pretty similar numbers. You can find the F naught here as well. It's like 2.5 times bigger. That's the original one. That's cutting off at 1. The new one may be cutting off by 2.5. Can't draw that. That should be about 5 here. Replace, so the work function is now about 2.5 times bigger than the previous work function. Let's have a look at the 6-mark question and then we'll move on. That hurts. Okay. Is one. Okay. So 1 is 5. Okay. Look at the 6-mark question. When you guys done, tell me. Go through the 6-mark question. Or maybe write the structure of the question. So when you're answering question 17, so you should go pick your choice. You need to state your choice. Then wave model prediction. Then you have to say how wave model failed by, so the experimental results. Fail to agree with wave model. Then the predictions in particle model. And how the particle model satisfactorily explain that. So that's what the structure is, prediction in particle model to get the full marks. Okay, so that your choice will have 1 mark and the other 5 marks will be gone between. This is the 6 marks question, guys, in page 10. Okay. So there are 3 choices. The 3 choices are, you have to select only one. One is the presence of threshold frequency observed in the presence of threshold frequency. That's the most common one. That's the most popular one to pick. The second one, the lack of time delay. no time delay. Third one, commonly you can take increasing intensity of light did not change the kinetic energy. The maximum kinetic energy of the ejected electron. These are the three choices. Or you can make more. These are the three main choices. You should know these things, and then you had to pick one. What year? This is 2018. 6-mark question was in 2018. Yeah, 2018. So it was Northern Hemisphere. I think there was a 4-mark question in week one. So quite possible to have a high mark question. Okay. So when you're writing, so maybe we'll pick the most common one as well. Presence of threshold frequency. So we pick that, and that's you get 1 mark, and then you have to lay out your answer. So the your choice. Let's select the presence of threshold frequency. Observation of threshold frequency. That's your choice. Then you have to lay out how the wave model. So wave model prediction and how that failed. The wave model predicted that the light carries, the energy of the light is proportional to the intensity. Amplitude or intensity or brightness of light wave. That's the first one. So therefore, all light should be able to eject photoelectrons. Regardless of the frequency. So that's a wave model. Okay, now we're talking about the results. The experimental result shows that only light with certain frequency and above frequency, we call threshold frequency, and above. And above, be able to, will be able to eject photoelectrons. Okay, photoelectrons. The light hit frequency below could not eject photoelectrons. Even the intensity was very high. Very high intensity. So that's the failure of wave models. You can't explain that. There is a presence of threshold frequency was evident. Now we're talking about particle model. That's the wave model. Now what's the experimental showing, results showing, and then how experimental results contradict the wave model. Now particle model, predictions in particle model. It predicts that so the energy of the light particles are proportional to the frequency. Or is whatever is related to frequency of light, not on intensity. Not on intensity. So only photons with high enough frequency so will have sufficient energy. Sufficient energy to release photoelectrons. You can mention that each photon giving energy to each electron. Because each photon can interact with one electron. And eject. Common back to a binding energy. So like just in general terms, you're trying to get electrons. So that's like a 6-mark question. Okay. All right, that's 2018. Okay, maybe we'll stop there. We'll focus on the last bit of things. Do you guys think that we went through enough matter wave type questions so we can just go to the last segment? But we'll finish it off and then we'll come back and revise more questions in different segments, different areas. Okay, the last section is Bohr model of atomic structure. Once you guys are done, tell me. Just quickly go through absorption emission spectra. That's where he was initially intrigued by that, looking at the absorption emission spectra. And by knowing that light energy is quantized, he's going to use that idea to construct a model for atoms. We know that his model was only successful like hydrogen. When you come to higher atomic number material, it didn't really work. This is where generally the Bohr model was kind of a semi-classical model, and then you had to bring back the wave model of particles to explain relatively, to make some corrections to his model. Even then you need to extend that further using that Schrodinger's equation. We're not talking about Schrodinger's equations here. Rather than orbits, then you guys can talk about orbitals. That you can give a probability where electron can moving around, but you cannot say an exact position where it can lie. So there will be theory question, most likely coming from this photoelectric effect, asking the failure of wave model and justify how the particle model explain the experimental results. It answer can vary, marks wise can vary from 3 marks to 6 marks. My just feeling is because they have taken off marks, questions, sections from waves, there's a chance they can increase some of the theory question just to, because they're always checking the theory question and then they hate to see, they call data dumping. I think I mentioned to you earlier. Just writing things directly from your cheat sheet, they not really like it. What you can do, you can make use of your cheat sheet as a guide, pick some points and then read the question and try to align your answer to the question. Okay.
Derek, could you post this on YouTube?
This, yeah, okay. I think
This
you asked
lesson?
something else. I think I forgot previous one too.
I think you posted it.
Okay.
Other one, I'm not sure.
Yeah.
I think you're pretty sure you did.
Okay. I was recording. Yes, I am recording. Okay. You guys done? Can we move on? I think there was another 4-mark question, as I remember. I can't remember whether it's related to matter waves or it's related to the photoelectric effect. I'll find that question as well. These are all recent exams because we didn't see 6-mark 5 marks question before 2017. These big massive number marks questions came in since 2017. But there were no big question last year. That doesn't mean that this year we can, like there were 3 mark questions, but not 6 mark questions. They can still put 6 mark questions for 5 marks. When you guys done, tell me, okay guys, we just need to move on. Okay, done. Anyone else still writing? Hey guys, now we almost coming to the revision stuff because I'm not going to drag too long saying revision. What I'm going to do is sections, like maybe go before we go for trial exam. So I'll go through main sections. Maybe it's like people are having trouble with special relativity or spring question or power transmission question or something. Maybe I'll quickly do a recap, background and the theory on that. And then we'll go through there. Otherwise, we have, although we feel like we have time, but the time will fly very quickly. Now, you guys in parallel, you need to work on the practice exams I send. It's a good one to start because it's not really new one, so relatively, it's a collection of 2012 to other papers, still valid stuff. This is a good one to revise. You don't need to stress out with your time that you spend on each paper. You don't need to stress out marks. You might not get like high marks, don't worry, but you need to understand the weak points of your so you need to get an Excel sheet or maybe Word document or notepad or maybe exercise book, write down the weak areas. So every time you do a paper or section, at least you need to see that some improvement, the stuff that you're learning. That's the main idea of this trial exam. Some people say I did 40, 50, 60 papers. But if you're doing the same error and you don't still understand that some areas, but there is no real use. If you're doing 40 papers, really good, provided that you have improved every single paper during every single paper. So as I said, just maintain that error book or error spreadsheet, error notepad or whatever. Just write it down, your weak area, the common silly mistakes you're making. Yes. So then you can improve every paper. Okay, maybe we'll move on. Now what Niels Bohr, his name is Niels Bohr, he was using, so people understood Bohr model was based on, he was extending the Rutherford's, the finding, because initially people thought the atomic structure was like a plum pudding, protons and electrons are spread around, and then Rutherford did the experiment shooting alpha particles through the gold foil, and then realized that most of the atom is empty. The nucleus is very tiny region, but your mass is concentrated in the center. Electrons are maybe around. So he's trying to extend that, but my model was based on absorption and emission spectra of gases, absorption and emission spectra. Obtained from various gases. So these gases could be hydrogen, it's a common one, could be helium, mercury, neon, and so on. As well as understanding that that energy of light is quantized. It's not a continuous, it's like a discrete quantized. Okay, it's like equals HF or epsilon lambda. Now, what is absorption spectra? I think you guys are covering these stuff. Absorption spectra. If I have, say, visible light spectra, if I have visible light, and if I have a spectrometer, simplest spectrometer that you can obtain is a prism. If you send the white light through a prism, you get the full rainbow colors. That's your spectrum. So if I look at a pure white light, I should get a full spectrum, continuous spectrum, rho G view, all the colors. But what's really happening, intriguing thing is, if this white light passes through some cold gas clouds, can you see that? White light is passing through some gas clouds. It's in your note, okay, in there. Then what, if you are analyzing that spectrum, you can see these black lines. Can you see these black lines, missing wavelengths? These black lines are corresponding to missing wavelengths. Why they were missing? Someone has stolen those wavelengths. That means someone has taken off those energies corresponding to that wavelengths. Okay, who is taken those energies? By the gas cloud. The important thing, by analyzing so many different types of gases, they realize that these missing lines are like a signature. It's like a DNA of that particular gas. If I'm sending this, I'm analyzing the spectrum through hydrogen gas. Hydrogen gas is own unique missing lines. If I'm looking for helium, helium has its own unique missing lines. Neon, it has its own unique missing lines. That's why these spectrums are quite important. So people can have a collection of these absorption spectra and keep like a bank, a library. Say if you obtain an absorption spectra from far distant star outside our galaxy, maybe, you can come up to a conclusion what kind of gas clouds or what kind of gases should be surrounding that particular star. Yes, quite useful. So same thing. At the same time, you can produce emission spectra. Emission spectra easily you can produce by emission spectra. So you can fill up the gas. Let's say this is the gas, you can fill that gas into a glass tube, sealed glass tube. You need to supply energy external. What's really happening in absorption spectra now, because after Bohr's model, according to his proposal, what's really happening, let's say hydrogen. Hydrogen has only proton in the center, nucleus. There's no neutron. He was saying that electron can occupy this allowable energy levels. He was saying allowable energy levels. Okay. Expanding that later on, they go into these shells, subshells, SPDF in your chemistry. We're not going that far. And rather than orbits, you go into orbitals, not going that far. So if I have an electron here, what's absorption means? It can obtain energy from external source, like say your white light you send through. You absorb that energy. If that energy matches exactly, that's the word, exactly, with the energy difference between this level, if I label that E2, that's E3, if the energy difference matches with the supplied energy by the external source. If that exactly matches, this electron can excite it. Because you have these certain allowed energy levels. That's why these allowed energy levels are very unique for each different gas. And that electron can excite it. So that absorption is marked by these missing lines. So if I am going through this different gas, okay, different white light going through, it's picking up, okay, which one I can pick up. If I supply more or less, it's not interested. You need to supply exact amount of energy, then it just, you have all the colors and suddenly it's going to absorb that line. On the other hand, emission means this excited electron is like a drunken guy. So it's gone high, it's gone to a higher level. It doesn't stay there. It doesn't stay there. You're going to come back. We'll talk about when you're coming back, you can have more than one path. For the time being, let's assume he's coming back to the ground state. This next day morning, he vomited, he had a bit of a, this headache, but it's all gone. Now he come back to his normal level. Back to normal level. During that process, he's releasing light. That's what we call the emission. This is emission. So that's absorption. During the absorption process, the electrons in the lower energy level, they jump into a high energy level. In the emission process, electrons in the high energy level come back to the low energy level. So the emission spectra, I can produce an emission spectra. These are the ones he's looking at. He was looking at, oh, that's hydrogen gas producing is unique missing lines. And also those missing lines are very consistent with the emission lines you get from the same gas. So this is hydrogen, let's say hydrogen. You got absorption spectra from hydrogen. Now you're going to produce an emission spectra from hydrogen. What you do, you apply a very high voltage. There are movable or free electrons here, but we just hide in that free electron part because we're not covering the energy supplied by the electrons in our year 12 level. Let's say the atomic electron means the hydrogen atoms are there. These electrons will gain this energy by these fast moving electrons. Let's say we just understanding purposes. So got that energy, we jump up and then it's coming down back again. During that process, you can easily make these emission spectra in the lab. And then look at his spectra and analyze and saying, oh, how consistent that absorption and emission. So he was using all this emission absorption spectra and then looking at the energy level difference. So looking at the color, oh, he's releasing blue color. He know the wavelength of blue and then work it out, okay, what kind of energy it's maybe releasing by using simply this equal to epsilon lambda. Using the quantized nature of light. And then they know, okay, the energy difference between the two levels should be that. That's how we decide in the structure of the, say, hydrogen, structure of the helium, structure of the mercury, and so on. Okay, so that's absorption. So I just need to give a bit of a more clear picture in terms of absorption spectra. So let's say you have this white light source, let's say sun, producing white light. Or visible light. So it's going through these gas clouds. Just put a different color. This is blue. This particular gas cloud. The reason they be saying is cold gas cloud. If the gas cloud has a very high temperature, the particles, like you guys learn about thermodynamics, they have high kinetic energy. They are less likely to stay in one place because the absorption cross section is very low. That means like you're shooting bunch of people into a crowd with a gun. Yes, let's say toy gun. This is bad to say it's using a gun. But if the people are running quite fast, when you're shooting, it's less likely I can hit these people, yeah? But if they are moving slowly back and forth, then I can hit easily. It's likewise, when you have a relatively cold gas, the white light can interact more easily with the cold gas cloud, atoms in the cold gas cloud. And then what do? You set up a spectrometer. This is on the ground, and simple spectrometer has maybe a prism. You can buy a very expensive ones. This is like a very simple one. So you can set up a telescope there, get more focus, and then the light reach in there. They're going through the kind of dispersion. You're producing a spectrum, and then you set up another telescope, and then you're observing it. So that's you observing, and then you get the full spectrum. This is a spectrometer, okay? Sometimes like you might wonder what that means. Spectrometer, like a simple system. So the light is split into different colors here, or dispersion. Now that's your absorption spectrum. Okay, that's the absorption spectrum. You get the full visible region, OGPU. I don't have all the colors, but just give us some idea. That's your red. It's ugly colors, but then you got a bit of orange there, green there. Make up our spectrum. And then the green. I don't have violet, I just extend that and do a bit of a just purple. Okay, that's your full range. And then now you see the missing lines. So missing lines are here. There's a one line missing. Maybe there's a couple missing there. Maybe some missing there, just trying to indicate that these black lines are, these are absorption, missing wavelengths. In an exam question, they can give you like, okay, these are the absorption spectra. They can give you some missing wavelengths, ask you to find from which energy to which energy level the electron has produced the transition, that kind of question. So missing wavelengths. So missing wavelengths are corresponding to corresponding to the energies absorbed by the electrons in the gas. Electrons in the gas. Okay. So these missing lines are very unique to each individual gas. As I said, it's like a DNA of that gas. You can recognize, oh, what that gas is. If there is unknown gas, if I get an absorption spectra similar to that, I can straight away say, yep, it's gone through hydrogen or it's gone through helium. Each individual gas. And then have a feel about what's that? Maybe gross. This is like we jumping, we kind of use in our Bohr model here, but for your understanding purposes, what's really happening? And the electron in the ground state or maybe low energy state, these are called low energy states. Close to the nucleus, the energy states are much more low energy. Low energy. If you go further close to the outer, like a valence electron, they have very high energy. So when you obtain this energy from the light, so it's absorbed, and then they absorb that energy, and then electron can excite it into a higher level. That's the absorption. Remember, I need to show that that's my absorption. Absorption, if you guys can't really see it, the red line numbers are saying absorption, electron absorbed into high energy level. It registered like a missing line. On top of that, emission spectra can be produced by the gas discharge tube or gas tube with high voltage. The high voltage to supply energy. As I said, the supply energy through electrons. High energy electrons comes in, supply the energy to these electrons in the orbits, and then they have producing the transition. Once they produce the transition, we can't see that missing lines, but what we can see, the electrons coming back to the ground state. Emission lines are produced by the release of energy during the transition during the transition of these electrons from high energy level to lower energy level. So sounds like release of energy. From the transition of electron. From high energy level to a low energy level. To lower level. So what you get here in the emission spectra, it's all blank, but we get few bright lines. Because we're not sending through white light or anything. We just excited these electrons into a higher level. Now they're coming down to the ground. So you see that line that previously was missing coming back. Here, there's another two there. Maybe another one there, and so on. There will be some additional lines. We'll talk about these additional lines we're getting. This is the emission spectrum. Everything blank, we get these distinct colors coming through. That kind of making sense, guys? Yeah. Emission spectra coming when they're coming down to the ground state. Absorption spectra when the electron excited to a higher energy state. Any questions on this? Something not clear? Then we had talk about the assumptions made in Bohr model. His initial assumptions are pretty simple. He was saying that electrons are orbiting around the circular path. So the gas tube is for supply, like this is the easy way to produce a spectrum, emission spectrum. So what you do, you trap the gas into this is like a neon lamp, okay, or mercury lamp. You supply, so you trap the gas. Yeah, so the atoms, so hydrogen atoms are there. Now, external energy supply by this high voltage, giving energy to these electrons. Electrons can excite it. Because the reason is, if I do this kind of experiment, I get the emission spectra and the absorption spectra together mixed up. I can't really isolate these two together. Yeah, this is a good way of isolating your absorption spectra. Because I can do the same thing like this. I can get a white light, send the light through this gas cloud and looking at the spectrum. Then what I get is absorption spectra. At the same time, some of the electron that excited might be coming down as well. And overall, I might probably not see that because they can mix up your emission spectra and absorption spectra can come in when I'm analyzing. Those electrons excited to higher level, they're coming back again. So when I do this way, I don't get any absorption spectra because I'm just have a trapped gas inside, I'm supplying energy and they excited within. Yes, so I'm not supplying energy externally, so I'm supplying energy through this high voltage and then they're releasing it. And then I can easily get that, the emission spectra in that case. Okay. Right, now we have to write the assumptions made in Bohr model. So what he was saying that the missing lines or existence of the lines appears in emission spectra is like a DNA of the gas, telling you the structure of the element. So based on that, he came up with his own model. Assumptions. Bose model of atomic structure. Some of the assumptions are reasonable. The main assumption that he couldn't explain properly was how the electron can sustain without losing energy when they're orbiting around. Because, as I said, did I mention that before? When you're moving an electron around a circular path, or whenever you accelerate an electron, you lose electromagnetic or lose energy as light. Yeah, that's how they produce electromagnetic waves, by accelerating electron. So when the electron going on a circular path, of course we know by our knowledge of circular motion, electron is accelerating. So he kind of made an assumption. It's combining a partial classical quantum model to overcome that idea. Okay, so one of the assumptions he was saying, electrons are orbiting around this well-defined circular path, the rings. That's where the term Bohr rings came in, yeah? Bohr rings. Because he is suggesting electrons are going on this circular ring-like paths called planetary model. We have this center, electrons are orbiting around. It's like a sun and the planets. What he was saying is electrons are orbiting around. Around the nucleus. In well-defined circular paths. Without losing energy. Without loss of energy. Because the argument was if the electron is losing energy, eventually it should attract back to the nucleus. If that's the case, atom can't exist. Atom can't exist. So atom can collapse, have to collapse. But we know that it doesn't happen that way. The electrostatic force between the electrons and the proton and the nucleus. Supplies the centripetal force. Okay, supplies the centripetal force basically. Okay, the charges are same. Q1, Q2 R squared. Okay, so the electron in a lower energy state can absorb exact amount of energy and excite it to a higher energy level. by absorbing the exact amount of energy. That requires for this transition. So basically trying to say that so when the electron is jumping into higher level from a low energy state, the amount that it absorbs should match with that energy difference. So if I say this is E3, if this is E2, so the absorbed energy or the energy provided by the external source should exactly match with that. You can't take more or less. You have to have that supplied energy should be exactly matching with the energy that you supplied. Okay. And also electron in excited state come back to the ground state, releasing that exact difference between the two energy levels. By releasing the energy difference between the two levels. The electron is excited here to come down. Say example, this is E2 is 6 eV. Let's put number saying 2 eV. 3 or something. So when you're coming down, the amount of energy you release, 6 take away 2, so that's 4 electron volts. So it will release that exact amount of energy that matches between the two. So that records as a emission line. And most importantly, one additional assumption he made was that the angular momentum, we'll talk about what the angular momentum is. Angular momentum of the electron is equal to multiple number of Planck's constant divided by 2 pi. So this is like you're bringing some classical and the quantum where your n equals 1, 2, we call later on principal quantum numbers. So when you say angular moment, I'm writing for a reason because this part is not really talking about in our style design, but there's a nice match to that. Because you guys know linear momentum, an object moving on a straight line, linear momentum is given by m times v. If some object is moving in a circular path, that's where we're talking about angular momentum. If the electron is moving, its angular momentum is given L is given by the linear momentum times by the radius. Times by the radius. So basically saying that mv times r, write down this relationship. Later on we'll find it. There's another guy, de Broglie, coming up. He's in a different way, completely different way. He's coming up with the same relationship. So this is why there's a weakness in his model, because they say that he was using maths to satisfy this condition, saying that it's not losing any energy. Because otherwise, everyone believed that accelerating electron should be losing losing energy. That's what they're doing in a synchrotron. What they do, they accelerate electron through a circular path, put bendy magnets. When you do that, it loses energy. We call synchrotron light. Okay, I think we can talk about last thing, energy level diagram. You guys kind of absorbing this, or you guys are emitting? Are you in the absorbing mode, or like a rejection mode at this moment at time? Okay, right. Let's get this energy level diagram. Then we have like a maybe half an hour things to complete next week. So get through, then that bit done. That's it. All right. Once you finish writing. See, bottom line, like what you guys need to understand, what is the absorption spectrum, what is the emission spectrum? If they give a absorption spectrum with a missing line, would you be able to find the wavelength? They give a particular wavelength, or maybe find that energy. Just say lambda equals 430. That's the missing line. So then they say, okay, you find the energy and look at which transition is corresponding to that. From here to here, something like that. Okay. When you're done, we quickly have a chat with the energy level diagrams. The energy level diagrams is what you guys definitely have in the exam question. That's 5,000% definite we have the question. Energy level diagram. When you guys done, tell me, okay? Don't stay there. Done? Done, okay. All right. How about the other guys? I'll see another done. If you guys done, then I can wipe it. Vitura, Yash, Sudesh, Sanaraj. Okay. Right. Now, energy level diagrams. Now, energy level diagrams are a way of representing this electron transition from represents the different energy levels within atom. Electrons can occupy, or electrons are allowed to occupy. In a given atom. Okay, now we'll take the example, simplest one, hydrogen. This is the equation that Niels Bohr is given for hydrogen. Each energy level can be represented by this number divided by n squared. You don't need that number. It's very handy for me because when I'm drawing that energy level diagram, I just follow that. Your n numbers are 1, 2, 3, and so on. So there is only y-axis. That's your energy. Now, in terms of the exam question, guys, energy level diagrams can start with the lowest negative value at the bottom, gradually going to until 0. First one will draw like that. The lowest one will be the lowest negative value. That's we call n equals 1. That's the lowest energy level. This is what we call the ground state. That's the most stable state for an electron, or lowest energy state. That's the one closest to the nucleus. Okay, n equals 1. If I put n equals 1, what I get here, one thing that you guys need to note is that's 13.6. These are in electron volts. When I put n equals 2, that's what we call the first excited state. It's like harmonics, excited state. You don't believe, maybe some people are referred already. You are bringing your standing waves again. You're bringing your standing waves again to these questions, okay? N equals 2, 13.6 divided by 4. That's 3.4. You can see that the difference is about 10.2. The difference is about 10.2. Now watch the difference between the next one, n equals 3 and n equals 2. Why I'm just trying to highlight these things, it comes very handy when you try to do the questions. Depends on the energy they're giving. The second excited state. When you have n equals 3, 13.6. This is only for hydrogen, guys. So 13.6 divided by 9. Plus I get 1.5. You can see energy is becoming bigger and bigger. Finally, this is 0. This is what we call ionization. If the electron in here, if the external energy is 10.2, that electron will happily absorb that and jump in here. If you supply 10.5, he said, nah, I'm not interested. Because you need to get that exact difference in the energy. Okay, keep that in your head. But if you supply 13.6 or more, it's happily absorbed and say, I'm leaving this atom. I'm not coming back anymore. It's become a free electron. But if the energies are different, like a matches in between, then it just excited and come back, excited, come back, excited, come back. Okay, so that's n equals 4 now. Your gap is getting narrowing now. The difference here is about 1.9. Previously 10.2, 1.9. Let's see 13.6 divided by 16. It's 0.85. You can see the gap is more narrowing. N equals 4. That's something that you need to keep in your head. By the time you reach here, it's almost continuous here. You can't even see that difference. So close. Okay, put n equals 5 as well. So the difference here, it's about 0.7-ish kind of thing, 0.7 like that. If you 13.6 divided by 25, you get 0.55. The difference is about 0.3 now. This is 0. And sometimes the other way of giving the graphs is you start from 0 and you go into more positive values. Ionization going to be 13.6. Remember, these are two different ways they're giving the energy level diagrams. Either you start with the most negative and go into the positive, or you starting from 0, that's quite very common, and then going back to 13.6. And that's 0.544. The difference is about 0.3. The difference about 10.2. Difference about 1.9. Difference about 0.7. Difference is about 0.3. You can see the gap is getting narrower and narrower. So at high energy levels, the energy difference between two adjacent levels become smaller and smaller. By the time it reach close to the ionization, say guys, maybe right, massive, latest is ionization. So it doesn't matter. Ionization. Smaller and smaller. Near the ionization level, energy levels are almost continuous. Almost. Still there is a discreteness. Almost continuous. Almost continuous. How are we going with the time? Okay. Maybe we'll stay there. We'll do a question next week. Few questions next week, energy level diagrams. Just to give you a heads up, if the electron excited to n equals 4, if they ask you to label the absorption, that's your absorption. Absorption always goes up. When you try to label the emission, guys, an electron excited to n equals 4 has 6 paths to come down. Okay, an electron excited to from ground state to n equals 4. N equals 4, that's a third excited state. Sometimes in the exam, they ask you to list all the 6. Six paths to come to the ground state. Let me just quickly write down and then just go. The 6 paths are, it can come straight down. Remember, it's not only one atom, there are so many of them. That's 1. This is 2. That's 3. That's 4. It's very common, they ask you to list all that. That's 5. And then that's 6. These are the all 6 possible paths. That's n equals 4 to n equals 1. The second one is n equals 4 to n equals 3. Third one, n equals 3 to n equals 2. Fourth one, n equals 2 to n equals 1. Fifth one, n equals 4 to, we're not doubling, n equals 2. And sixth one, n equals 3 to n equals 1. These are the 6 possibles that they might ask you to list it. So you need to get the energy difference, energy difference, energy difference. They're not giving massive marks. They might be given 3 marks for that. The second, what is the last word? It is underlined. Continuous, okay? Continuous. Almost continuous. Almost like adjacent to each other. Keep that in mind. The difference is getting narrower and narrower. It's very, very helpful when you're doing the questions. Okay, any questions, guys? Anything we need to run through? If not, just copy it down and then I'll leave you guys. So there is a formula to figure out the number of parts. Yeah, some people are coming out like there's no proper, like if you guys can work it out, one, that would be nice. If people try NPR, NCR, seems not working. Someone said that you rather than getting to number 1, you can get up to second excited state or something. Yeah. So your permutation compilation, this doesn't really work. Maybe it should be working, but I don't know. Factorial 4 divide, no, it doesn't work. It doesn't work. If you can figure out, yeah, tell me. NPR, NCR thing. The other thing is, now I email you the people who haven't done the test, please do it. The trial exams, I just send you the link before earlier. If you guys are not in a position to print it, I can print it. I don't know how much I had to post it. I don't know the cost. If the cost is not too bad, like under $5, I can post it. If anyone wants it, if anyone can't print it, let me know. I really want you guys to start working on these trial exams because those are good ones as a revision material. Once you get up to the speed, we can start doing the actual trial exams. Yeah, one kid I was asking about the page 400 and something question. So that's exciting. That means he's done that many pages so far. Anyway, so I'll let you guys go. Any question? If we don't have any questions, let you go. Okay. Okay. See you guys.
Thank you, sir.
Yes.
Thank you.
Thank you, sir.
Bye. Bye.
Thank you, sir.
Bye.
Thanks, sir.
Bye. How is Rasinda going?
Yep. So could you make sure you put this on YouTube, please?
Yeah. Okay. Okay.
Thanks, sir.
Why you couldn't write it down?
Nah, I did. I wrote most of it down, but I had to go for like 5 minutes in between.
Okay. Okay. Yep. I'll send you. Okay. See you guys. Bye, Rehan.
Yes, yes, sir.
Just wanted to just ask you how you going. That's all.
Yeah, I think I'm okay.
Yeah. Give it a try that test, okay?
Yeah,
Don't-
I just haven't finished it yet. I've got a couple left.
Yeah. Because it kind of give you a kind of indication.
Yeah,
In terms of trial exams, you manage to print it out, or you have enough papers to start it? I would say like you start it. You might find it is so difficult at the beginning. That's normal.
yeah,
So so don't give up. You can post me. You can email me. Just get the picture of that page. I think you had to find some sort of strategy to work. Okay, so we have a few weeks left now.
yeah,
Don't hesitate to ask questions. Okay, maybe do the test, and then that will give you some indication how you're going. And then I would suggest that you start doing that practice exams as soon as possible.
Mm.
Okay, don't wait until like close to the exam or anything.
yeah.
Do you think any area that you need to work on more?
For the exam,
Yeah, in like stuff that we learned so far. Do you think there's a particular area that you need to work on?
maybe just some motion stuff, but other than that, not really. Nothing specific, but
Okay, motion. Okay. But apart from that, you kind of okay.
yeah, I think so.
Which SAC you got the lowest marks?
I'm not too sure which one.
Okay. If you can just maybe just stay another couple of minutes next week, just tell me which SACs you didn't do that well. At least,
Let me see. Let me just check now.
yeah, okay. Then I can give you a bit of a. We can have like a small, quick session, one-on-one, like just 1 hour, half an hour. If you can, there's some kids doing that. Say that, okay, I did some questions, so I don't understand this one. So it's not hours, just very short time. Because we had to get through this, Rehan.
Yeah.
What's your overall SAT marks are like? Do you have a feeling?
They're okay, but I think, I'm looking at it now. One called data analysis wasn't.
Okay, data. Was it in a particular section, or what? Which section of questions you got from the data analysis?
For that SAC?
Yeah, is a power transmission? Oh,
Yeah, I think it was.
okay. So what we can, because data analysis type questions, we're going to go through like a drawing graphs, getting quantity. So we have to go through those ones. Okay. Do you think that you understand in the concept we talking about in the class? What do you think?
Yeah, I think so.
Only thing that like you have to find a time to do some questions, right?
Yeah.
Yeah. Okay. But just tell me whenever if you need like some help, like half an hour, we can have a quick Zoom link and then have a chat and sort out
Yeah,
some.
sure.
Okay, but you need
Okay.
to start your call. Yes, you need to be proactive.
Yeah.
Okay. Yeah. Some kids are doing that, so you had to do the same thing.
Yeah.
So we'll get through these few weeks. Yeah, maybe 8 weeks or left. Not many.
Yeah.
Okay. I'm happy to help. So if you are doing your part, okay.
Yeah. Thanks.
Okay, no problem. Just stop there. Okay. See you then next week.
All right. Thank you.
Bye.
Bye.